was a neutron star. I mean, at the end of the week, you will know everything if you follow his course.
All right, we'll try our best here. That's right. So it's my pleasure to be here, and these are very exciting times for us in LIGO and Virgo, as you all know. Of course, let's see. There we go. We had a very active second observation run that finished with the detection of 10 black hole pairs and 1 binary neutron star pair, which, you know, if you're here, I'm assuming that you've heard of all of this and you're excited enough that you're here, signed up for this course. So I won't go into details of the science and all the interesting scientific richness beyond this detection, these detections, but just to say that these are very, very active times. We had this very exciting second observation run. We're currently in the third observation run where we are detecting around 1 pair of binary or black holes per week and 1 binary neutron star system per month, more or less. So there's a lot going on, and there's a lot of science, and so it is my pleasure to try to bring you into the inner workings of how we actually manage to detect these signals, analyze, understand what they're telling us about their sources, and be confident that we can extract the most science out of them. So for this mini course, the sort of goals I set up for you, sort of arbitrarily, I guess, is to gain an understanding of how LIGO and Virgos are able to detect signals and appreciate the complexity of the instruments and the detection process that comes and enables the having signals in the first place, and how that impacts and should impact your understanding of the data and how you manipulate it. You should also come out with an understanding of the basic gravitational wave properties and how that gets impacted onto the signal morphology, so the properties of the signals that we'll be seeing, and also understand the second component here, which is the noise that comes from the detectors and their environment, and how that gets added to the signal, and how we can use the statistical properties of these random processes to actually make sure we're extracting the information about the signal in an unbiased way. Finally, there's a more hands-on component to this, which is that you should be able to, at the end, be comfortable accessing and manipulating the data that LIGO and Virgo make public for you to use. So we are making public basically all of the important data, not only around the detections, but also just whenever we're observing it in the instruments that we're operating under nominal conditions, we're making that available to the public, and there are many resources that we make available to you online, so that you can go on and carry out your own, reproduce what we have done, or carry out your own analysis, and so that should be one of the outcomes of this. All right, so more specifically, what I'll be covering in these 5 lectures is, today I'll just give you a primer to gravitational waves and their detection, because it's the first lecture of the course, so I'm taking it upon myself to introduce the field, if you wish. Then we're going to go over the statistical and physical properties of LIGO and Virgo noise and how to access open data. We'll do that tomorrow. We'll then dive into the studies of compact binary equiescences, so signals from binary black holes or binary neutron stars like the ones we have seen. We're going to look at their signals and how we search for them. Then we're going to look at how we actually extract information about what source produced them once we've seen a signal. And finally, we're going to branch out and look at the kind of analysis that we do searching for other types of signals that we haven't seen so far. Okay, so let's dive in. And before I move on, let me say, you should feel free to ask questions. It's not that many of us, so it would be helpful if you want to raise your hand and we can go over some point that you have questions about. That's good. So I'm going to start with some basic overview of what gravitational waves are, just the basics of what's important to understand the analysis that we do. The details are going to be covered by Mario in a different course, in this different set of lectures. So I won't give you all this theoretical infrastructure. He will be covering all that, but I'll just highlight some of the main results that we need to before we start actually working with the data at all. Okay, so there we go. gravitational waves are solutions to the vacuum Einstein field equations, which if you've seen before, they are here. If you haven't seen before, you shouldn't worry about it. The left-hand side really just says, represents the curvature of space-time in some region. The right-hand side represents the stress energy density in that region, and what the equations are saying is that the two are proportional to each other. A vacuum solution means that this part is zero, so when we're working with the propagation of gravitational waves, we will have this side, which is Riemann quantity, is equal to zero. Again, Mario will go over the meaning of this, but basically what I want you to get out of this is just what the message is. The curvature of space-time is proportional to the energy density, and then you can have self-propagating solutions to these equations, just like you have self-propagating solutions to the Maxwell's equations in vacuum, which give you light. In this case, these are metric. In the case of gravitation, we're talking about perturbations, not of the electromagnetic field, but of the gravitational field, or of the curvature of space-time. And these perturbations may follow a wave equation, and that's what gravitational waves are. These objects, these phenomena carry energy and momentum from their source, just like electromagnetic waves do, and we can detect them and try to learn about the source by looking at their properties. Okay, so Mario will cover the details behind this. I just want to give you some intuition as to what the effect of gravitational waves are and how they're generated from a more intuitive point of view. So there are two things to keep in mind if you want to gain some intuition about what the effect of a gravitational wave should be. So if a gravitational wave is going through you, what should that do to you and your surroundings? Well, the first thing to keep in mind is the equivalence principle. So gravitational forces couple universally to anything that has stress, mass, energy. So you cannot really make any experiment that detects an absolute gravitational field. We can, however, detect changes in gravitational field. So I can say from place to place there's a differential. So we can measure the gradient in a gravitational field. And that's what a tidal field is, or what tides are. So you should be familiar with tides from, for example, the Earth-Moon system, and you know that because the Moon is pulling the Earth stronger on this side, you get this characteristic strain pattern that causes the actual tides in the ocean to happen. And so you see that effectively it's like stretching the Earth along this axis and squeezing it in the perpendicular direction. And this is the characteristic of a tidal field. So the change in space over of the gravitational field. This is really just what gravitational waves are. So as a gravitational wave goes through, it's perturbing this tidal field, if you wish, in a Newtonian language. And so what it will do in one moment is it will stretch and squeeze me in a vertical direction, stretch me in the vertical direction and squeeze me in the horizontal direction, and making me tall and thin, and the next moment doing the opposite, making me fat and short. And as the gravitational wave goes through, it oscillates between these two pictures with some characteristic frequency, for example. If you arrange a series of rings in space, of free-falling rings, and you have a gravitational wave propagating along the axis of the cylinder that those rings define, then you would see the stretching and squeezing in this way. So as the gravitational wave propagates this way, it's stretching and squeezing the rings transversally to the direction of propagation. So gravitational waves propagate at the same speed as light. We usually say gravitational waves propagate at the speed of light, but light, I mean, you could also say light propagates at the speed of gravitational waves. Okay, there's no more one is no more fundamental than the other. And their effect is to stretch and squeeze space transversely to the direction of propagation. And this effect you can always decompose into two polarizations, just like for electromagnetic waves, you have two polarizations, let's say vertical polarized light and horizontally polarized light. In gravitational waves, the two polarizations will be stretching and squeezing, let's say, along the vertical and horizontal axes. And that's what we call the plus polarization. And then we have the cross polarization, which is the same effect, but rotated by 45 degrees. And you see the quadrupolar nature to this effect which has deep implications. Yes. No. There are a lot of frame-dependent things, but we can always write down observables that will be independent of frame. So how you explain what this effect is will depend on your frame and your gauge. I'll come back to this a bit later. But what you actually measure, everyone agrees. Okay, it's like the usual thing in relativity. So maybe the description of space contracting or things moving, different observers might disagree what's going on, but they all agree what the observable is, and they will all agree that there's some effect like this. But I mean, it wasn't clear for a long time in the history of the field that gravitational waves weren't just mathematical fiction, and it wasn't just something that the math seemed to show, but it wasn't just the coordinates, but in reality it is a physical effect that does carry energy and so on, we can measure it. Yeah, that particular form, to make it look like that, you need to pick nice coordinates that make it evident then that you have something like this. But it won't change the physics. Yeah, but again, Mario will cover the details about gauges and so on, I assume. That's right. Yeah. Yeah, that's right. I mean, I haven't introduced that language here, but you have the curvature. Everyone agrees what the curvature of space in that location is. That gives you the Riemann tensor, that gives you the components of the acceleration of this. As long as you're in a frame small enough that you can apply the equation of geodesic deviation, you can use it. Which will be the case for as far as we're concerned. So these two polarizations, mathematically, what's going on is that any gravitational wave h, so h will be the strain, which is the basic quantity that we work with, and represents this change in length over length. We'll come back to this. Any gravitational wave we can decompose into two polarizations, plus and cross, and the effect of the stretching and squeezing in two perpendicular directions you can encode into tensors, okay, which in a given frame and in a given gauge you can write as for plus 1 minus 1 here along the diagonal, and cross 1, 1. So each column and each row represents the x, y, and z, x, y, and z. Okay, and so what this is saying is I'm going to stretch along one direction and squeeze along the other one. And what this is saying is the same thing but 45 degrees apart. Okay, so this quantity, the strain is just the changing length over length. So if I start with in these pictures I've been showing you, if I start with a circle and a gravitational wave goes by and it stretches it in the vertical direction and squeezes it in the horizontal, there will be some change in the original radius of the circle, and so you can see, you can determine how strong a gravitational wave is by looking at this ratio. So the first thing to keep in mind here is that this is an effect that's, the changing length is proportional to the length, right? So if I start with something that's twice as long, then the change in length will be twice as big, which matters when you're trying to measure these things. So you want to start with a big L so that the changing in length in absolute terms is itself bigger for any given gravitational wave. I'm sort of flying over this because I assume that most of you have some intuition, understanding of this already, but feel free to slow me down or tell me to speed up. Okay, so how strong this should be for a lowbrow analyst? You can just, like me, you can grab Einstein's equations. This is written in a different way as I showed before, but it's the same thing. Curvature and the stress energy density in space-time. The two things are proportional to each other. But if you plug in some numbers, let's say in SI units, you get that the proportionality constant is an extremely small number. Okay, that should already be telling you that to curve space-time in any meaningful way, whatever that means, you will need a lot of energy to do it. So space, in some way, it's hard to bend. Okay, so what you can imagine that this means that we won't be having gravitational waves of a huge magnitude, it will be constrained by this fact that like space-time doesn't like to be bent. And we'll see that the effects, generally speaking, of any physical gravitational wave are extremely, extremely small. Okay, so how do we produce gravitational waves? Again, this will be, you'll get more details and more rigorous treatment with Mario. But just to start with an analogy with the electromagnetic case. So what we want to have a wave is to have a time-varying source that produces a field that falls as 1 over r, right? That's sort of like what we define to be the radiative part of a field. So in electromagnetism, you can start, well, can I create an electromagnetic wave with just a monopole, a single charge? Well, it doesn't work because, okay, the first part of the static part of the field goes as a charge over r squared, and then if I make the charge change, if I could do that, then it would bring down an r, and it would go as 1 over r here. But you can't just make one single charge change because there's conservation of charge. Okay. So you can't use the electromagnetic monopole to create electromagnetic waves, but you can do it with the dipole. So if you start with 2 charges plus minus, the dipole or the static field goes as r cubed. You take a derivative, you get r squared. You take 2 derivatives, and you get 1 over r. And this is a time-changing radiative field that falls as 1 over r. And that's what basically we usually have with dipole electromagnetic radiation. So you can see that conservation conservation symmetries sort of tell you how you will be able to create waves in electromagnetism. And the same argument you can carry over to gravity. The main difference to keep in mind is that instead of working with the gravitational field, like we were working with the electromagnetic field in the slide before, you want to work with the gradient of the gravitational field, because again, there's no meaning in relativity to an absolute gravitational field, so we're going to work with the gradient. So G prime is the gradient of the gravitational field. That will be the basic quantity. So you want to have a gradient of a gravitational field that is time varying and falls as 1 over r, and that gives you the radiative part. So the same thing, if you want to start with a single mass, then the gradient of a single mass will fall as r cubed. If you take one derivative, you get r squared, but you can't do it because mass is conserved. So you stop here and you try to dipole. Okay, so two masses, or an excess of mass and a lack of mass, I should say, like plus and minus. The dipole, the gradient of the dipole will fall as r over r to the 4th power. Then you take a derivative of the dipole that falls as cubed, and 2 derivatives are squared, but you can't, because 2 derivatives of the dipole moment is actually momentum, and so that's also conserved. And so this is 0, and as this was 0. So you have to go 1 multiple higher to the quadrupole. So you can imagine a mass quadrupole looks like an excess of mass, an excess of mass, a lack of mass, a lack of mass, so 2 dipoles, okay? So this could be, for example, a binary, where you have 2 objects and no objects here. And in that case, it works, and you have to take several derivatives, but in the end, you get something that is time varying and falls as 1 over r. So this already tells you that gravitational wave generation will depend on the quadrupole moment of the time varying mass distribution. You'll need something, an accelerated quadrupole moment, to get something that gives you the radiated part of the field. No, there's no conserved quantity. I mean, in gravitational waves, you can have generation for quadrupole and higher. It's not just quadrupole. Is that what you mean? Yeah. Yeah, I don't know. Do you know? Well, again, this is my main goal with this is just to draw some analogy. If you have familiarity with how we do this in electromagnetism, you should feel that the gravitational wave generation process is not as exotic, that it has parallels with it. And there are nuances here that I will not go over and I'm not an expert in. But anyways, from this you get that this tidal field will go as that. From the tidal field, you can actually get this quantity that we have been working with before, the strain. They're separated by two derivatives. So this quantity G prime, the gradient of the gravitational field in Newtonian terms, is like two derivatives of the strain. So you see that actually the amplitude of the gravitational waves, when we are talking about the strain quantity, which is what we usually do, which is the changing length over length, that will go as the accelerated, so the two derivatives of the mass quadrupole moment, okay? And there's proportionality constants, and it will force 1 over r, where r, big R here is the distance away from the source, which is what we wanted by construction. Okay, all I wanted to say, really, this leads you to the fact that you'll need some asymmetry in you need some time-varying asymmetry in your mass configuration. And the prototypical source for gravitational waves, just like the prototypical source of gravitational wave is the electric dipole for gravitational waves, is the quadrupole. For these symmetry reasons, you can argue that. And that would be the binary system. It's the quintessential gravitational wave source, where you have two objects gravitating and rotating around each other. And you see this is a quadrupole because, again, there's an excess of mass here, an excess of mass here, a lack of mass here, and a lack of mass here. You can think of this as being a negative, a lack of mass is like a negative mass if you renormalize everything. Anyway, so for this quintessential prototypical gravitational wave source, you have a gravitational wave signal that's emitted at twice the orbital frequency. You can see that from the symmetry of the system, right? If you have two masses very far away and they are aligned, it will look the same no matter which one is in front of the other. So it should be that you have the frequency of the gravitational wave, the effect to you far away will look the same. So there's no, from the quadrupole radiation, you will get something, a gravitational wave that's as twice the orbital frequency. Then the strain amplitude will go like something that's proportional to the masses, inversely proportional to the distance to the source, and inversely proportional to the distance, the radius between them. And then there's some more complicated expression for the radiated energy in gravitational waves, but the main point is that you need a lot of mass in a small space to get a large gravitational wave amplitude. That is, we want compact objects to have this, to be able to have the strongest gravitational waves that we can. So a lot more mass in smaller spaces. It doesn't get more compact than black holes, okay? So these are the objects that can pack the most mass in the smallest space, and so they can orbit each other very closely and very fast. And it's not surprising they're intrinsically one of, if not the loudest, sources of gravitational waves, okay, definitely from the ones we have seen. And it was the first kind that we detected, like the case of GW15914, our first detection, which is represented here by this visualization of a simulation for numerical relativity. And in that case, we had two black holes. Each of them, one of them had 35 times the mass of the sun, the other one around 30. At the peak, at the strongest part of the gravitational wave emission, right before they collided with each other, they were going a bit over half or 60% of the speed of light. And this source was around 410 megaparsecs a wave, so very far away. So this has to be very loud so we could see it that far. In around 200 milliseconds, there were around the equivalent of 3 solar masses radiated away in gravitational waves. So that's equivalent to this kind of radiated power that's brighter than all the stars in the visible universe, as we'd like to say. But by the time this got to Earth, they were very weak, and their peak, the strains, changing length over length, was around 10 to negative 21, which just, if it gives you an idea, it's like changing the distance from here to Alpha Centauri by like the width of a human hair. Okay. All right, black holes are not the only sources that we have seen or that we expect to see. With binary black holes, similar to binary black holes, we also have seen binary neutron stars. So instead of having just vacuum solutions to Einstein's equations, there's also matter in those objects, exotic matter, and these as you may have seen, these objects can also smash against each other, producing gravitational waves, but also a plethora of electromagnetic emission because there's stuff there. Okay, so we have seen the first event like that, GW 170817 that we saw. We also detected throughout the electromagnetic spectrum with follow-up observations by over 70 telescopes. We can also expect to see, besides compact objects, compact binary coalescences, we can expect to see gravitational waves from supernovae. We can expect to see gravitational waves from isolated neutron stars that have an asymmetry in their moment of inertia. We can expect to see gravitational waves from the addition of a bunch of these sources that are very far away together that yield a random signal, which we call the stochastic background. And we may even get gravitational waves from more exotic objects and systems like dark matter or cosmic strings or other exotica. Okay, and there's several models for how to do that. So I'll go into a little bit of detail into each of these. All right, so the first, we organize these roughly by the morphology of the gravitational wave signal that they produce, how they would look like in the detectors, which will then determine the techniques that we use to extract them and understand them. So the first kind, and the most prominent kind, includes the binary black holes and the binary neutron stars. It's the compact binary coalescence. We have this very specific term to describe what these systems are. Okay, compact and binary should be obvious. Coalescence is maybe a little bit less clear, but it's a word designed to mean the spiral, so the part where the two objects are slowly spiraling towards each other when they merge, and when there's a final product that quiesces and radiates away imperfection. So the word coalescence is meant to stand for spiral merger and ring-down of this binary system. Besides binary black holes and binary neutron stars, you could have a combined system, neutron star black hole system, in which you have one component being a black hole and the other one a neutron star. Okay. All of these objects have in common a basic morphology. They produce a gravitational wave that has an increasing frequency and amplitude. So it gives a signal that we typically know as chirp. So we go like whoop, okay? And it will be short, so we call it a transient. Short here, there's two relevant timescales that define what short means. I didn't put that up here, but it's important, so write it down. So short, gravitational wave is short when its duration is very small compared to the rotation of the Earth, so that we don't have to worry about changing the detectors moving with respect to the source as the signal is happening. And it's short when it's we can assume that the detectors are not changing during its duration for all intents and purposes, so that the detectors are stationary and produce noise that have well-behaved properties over the extent of the duration of the signal. These systems are some of the best understood. We can solve Einstein's equations for the most part, especially for binary black holes. It takes supercomputers, and it took many years, but by this point we understand very well what these signals should look like. Once you throw matter in there, things get more complicated, but for the intents for the intent of the purpose of detection, then we know what this signal should look like, and we can use this knowledge to pick them out from the noise more easily. So just in the same way as if you're in a crowded room in a party that's very loud, but someone just speaks your name softly from very far away, you can immediately pick it up. It's the same concept that allows us to, something that we know we're expecting, extract it from the noise even if it's weak. And we take advantage of that to detect these signals. Again, a signal like that this is something, this is what it would look like in the time domain. So in the x-axis you have the time, and in the y-axis you have the strain. Okay, so it increases in frequency as the two objects get closer to each other. Eventually they merge, and then they produce a final object that settles down into, in this case, a final black hole, because this is a reconstruction of the signal from our first detection. And this is what we call a chirp. Questions? I mean, we'll come back to this over and over again. All right. You can imagine that there are all sorts of signals that we know should be there, but we don't have very particular specific models for them. That's the case for signals from supernovae, in which the actual gravitational wave signal depends a lot on the details of the hydrodynamics and magnetic fields or whatever other physics, neutrino, that is going on in the exploding star. And you have different simulations that include different components, and they produce slightly different expectations for what the gravitational wave should be. And so we don't have a very specific model of what that should look like. You can also imagine having more exotic objects that produce short gravitational waves that we haven't produced templates for, and just in general unknown sources that we're not expecting. So if you want to detect something that we don't even know it's out there, I don't know what it looks like, you need to have some sort of search that is able to pick out signals even when you're not expecting them. And that's what these model burst searches do. So they are short signals, but they will show up in all the detectors, as we'll see later, in a coherent way, and this allows us to distinguish it from noise, even if we don't know exactly what to expect. This is an example that I found just to show you several different possible supernova waveforms, again in time and strain. And so you see it's like they differ a lot and they're very messy, okay, and we don't have very specific models for them. Okay. The last two sorts of big categories of sources are very short, as I mentioned. We call them transients. But we also expect to see signals that are persistent, that last a very long time. Okay, and that's the case, for example, for a signal from a neutron star, so just grab a single neutron star, and this object is almost a perfect sphere because it's so compact and it's under so much internal pressure. But it's likely that there be some imperfection on its crust due to, for example, a very strong magnetic field at the poles or accretion or whatever it may be. And if this object is not perfectly symmetric, there will be some changing mass quadrupole as it spins around very fast. So for example, one of the most famous pulsars, the Crab pulsar, it rotates at 30 hertz. So it's an object that has 1.5 times the mass of the sun, rotating 30 times per second, okay? And so any small asymmetry will cause it to radiate gravitational waves. The signal you expect from a system like that is almost exactly a monotone. So it will be a gravitational wave that has contents almost exactly at a single frequency. It will not be this quick rising chirp that we saw before for the compact binary coalescences. It will be just boo, and it will be on for a very long time, effectively forever as far as we're concerned. So in this case, you can no longer make the approximations I mentioned before that the Earth is not moving and the detectors are stationary and so on. So the kind of analysis that we do to search for these signals is very different from what we do for other signals that we have seen. Besides neutron stars, you could expect these kinds of sources from particular ultralight bosons around black holes. I won't go into the details. Or again, you could have continuous signals from processes that we still don't know. So we search, we have different kinds of searches for these signals. In some cases, we target particular sources. For example, we see there's a pulsar there, a neutron star. We can direct a search at it and try to see if there's a gravitational wave coming from that direction. Or we can make a search that is agnostic as to where it's coming from and what properties it has. It's just looking for these constant monotones in our data. And these come with different associated computational challenges and so on. But anyways, what we're looking for is basically a sinusoid. Okay, all of the sources that I mentioned so far have the common properties that they are, in some sense, deterministic. We have a model for what this phase and amplitude of the signal will look like. We have a waveform. Okay, this is an important word. Yeah. Yeah, it depends on what specific mechanism is causing it. So there's several ways in which we can imagine these neutron stars producing continuous waves like this. They will all depend on the detailed properties of the nuclear structure. So yes, definitely detecting those waves will inform us as to nuclear physics. Whether it's from the inside or the crust will depend on whether it is the simple mountain on the sphere that I mentioned before, or whether there's other pin superfluid inside, or other more intricate effects in the structure. Like it could be what we call R modes or G modes, or modes of oscillation of the star itself that produce gravitational waves at not twice the spinning frequency, but 4/3 or even higher. Anyways, there's a lot of different mechanisms that could give rise to a monotone from one of these sources. Detecting that would be very important for nuclear physics and the equation of state in particular, depending on which kind of process it's causing it. One thing I didn't mention is that these signals, they're allowed and expected to slowly increase in frequency. They're not a perfect monotone. But if you imagine you have a rotating neutron star that's emitting gravitational waves very weakly, by the way, so these signals will intrinsically be weaker than those from compact binaries, for example, although they're on for a very long time. As it does that, the system loses energy, and because it's losing energy, will slow down, okay? And because it's not gravitationally bound in this case. And so the frequency will decrease very slowly over periods of months or whatever. And we see this happening, but by the way, with electromagnetic observation. Okay, so all these signals so far are deterministic. So we have this waveform, we have a template for what the strain as a function of time looks like. We can follow the phase as a function of time. Okay, we can trace what the signal is doing. But there's a kind of source that it's intrinsically stochastic, we call it the stochastic background, okay? And that means that the gravitational wave amplitude arises from a random process, okay? It's not following a coherent template from time to time. At each time, the specific amplitude will be a random number, essentially. But this random process will have specific properties depending on how it's produced. Okay, so one way in which you could have a signal that basically looks like noise, okay, is if you grab many of these compact binaries, place them throughout the universe, most of them will be too far away and too faint to individually resolve, okay? So in the same way, again, if you imagine you're at a party or you're in a room and you're talking to someone, you can identify exactly what they're saying. If you have 500 people in the room, it will just sound like noise, okay? So when you add a bunch of individually coherent signals in an incoherent way, you will get something that altogether sounds like noise. And you can have that in our detectors just from the incoherent addition of a large number of these compact binary sources throughout cosmic history. So all these weak signals reaching us, they arise in the detectors like a noise floor, but it's a noise that it's coherent in all the instruments, okay? So all the different instruments will be picking out this zzz in the background, okay, in gravitational waves. So again, one way which you can produce that is just from having many, many weak sources, okay? you can also have stochastic gravitational waves that are intrinsically stochastic. So for example, in the early universe, cosmological processes may have caused the emission of gravitational waves that are random by nature. And so we talk of astrophysical stochastic backgrounds, which means it's just from the addition of all these astrophysical sources like compact binaries, or primordial or cosmological backgrounds, which are signals that would be intrinsically from a random process in the early universe. By definition, these signals are broadband, which means they happen in large swaths of frequency. They're persistent, so they're all the time, and they come from everywhere, essentially, in the sky. So, just to review, we have transient sources, which includes the well-known compact binaries. It could also include signals that we don't have models for, like signals from supernovae or other more extreme objects. These are all of these have in common they're very short and loud. Then we can have continuous sources from things like pulsars, which are weak, but they're on for a long time, and they have a very specific frequency. And we can have stochastic signals that don't have a well-defined waveform. They're a random process, but they happen at a large band of frequencies. They're all on all the time, and they don't come from any specific point in the sky, but from all over. Okay. Are there questions about this general nature of overview of what gravitational waves are and how they can be produced? Yes. Yeah, you don't understand because I didn't say. So that's good. It's not one of the mainstream things that we look for, but there are specific scenarios that you can concoct that either dark matter would interact with the detectors directly, or you would have, for example, large amounts of some structure with a quadruple moment that radiates gravitational waves, and that could be detected. For example, if dark matter was an ultralight boson, this is one thing that has been in the literature recently very popular. You could and you start with a very fast spinning black hole. Then this hypothesized dark matter particle will spontaneously, if it has a mass of the right value, it will pair up with the black hole, and it will spontaneously grow a condensate cloud around it. So there will be a cloud of dark matter around the black hole that has around 10% of the mass of the original black hole. It extracts energy from the spin of the black hole, and it forms very rapidly, and then it sticks around for a very long time, emitting gravitational waves. So that's one mechanism. But there are many other. These are not like standard things, but we can imagine that there are ways in which we could find traces through gravitational wave observations, so dark matter processes. But again, it's sort of out there. We can talk about it more later. I think it's fun, but maybe no one else does. Are there other questions about this? Yes, in principle, it's all in there, but the fact that they all have very different morphologies allows us to separate them from each other. I mean, so far we have only detected signals from binary black holes and binary neutron stars. We haven't detected any of the other kinds that I've described, although we are looking for them. That we haven't seen the others? Yes. I mean, it's not surprising if disappointing, but if given the distribution of objects and sources, yeah. And we will cover some of these things later on, like how we actually pick out these signals from the data. And you're right, it's all in there together and mixed with noise. So how do we do that? And maybe I'll say something about the expectation of the rates, but probably not too much. Another question? Okay. So how do we measure these gravitational waves? You have an idea of how the physical processes that generate them and their properties locally as they travel through space. How would you go around actually detecting this phenomenon? Well, you can't use a ruler. if you tried, the ruler would get stretched and squeezed with the passing of the gravitational wave, and you would not be able to notice that anything's changing, right? If I start with a ruler, let's say a meter stick, and the gravitational wave comes and it squeezes it, it will still read 0 and 1, and if it stretches it, it will look the same. Locally, I can't use that to measure the gravitational wave. So instead of using a physical ruler, we can use light as a clock, in a way, okay, to try to measure the proper distance, the effect of the gravitational per distance between 2 points. I'm messing up the microphone, all right. Okay, so for the technically minded, in the TT gauge, the gravitational wave doesn't change the coordinate distance, but it does change the proper distance, and so we can't use a ruler. We have to use something that changes, that is sensitive to the proper distance between 2 points. That's what interferometry is, and so I'll show this video that you may have seen before. You grab a laser, you split it into two, it travels down two orthogonal paths, it bounces back to mirrors in the end, and then it gets reconstructed here. And so you see, okay, you have two beams, they have some phase. Just bear with me, it's slow, okay. It gets reconstructed in the center such that there's a phase flip and the light cancels and there's no measurement out this readout photodiode on this side. If a gravitational wave or whatever other phenomenon changes the relative length in the arms, this cancellation will no longer happen, and we will measure something on this end which we can turn into a digital signal that encodes the gravitational wave as it passes. That's the basic idea behind LIGO and Virgo, which LIGO is a laser interferometer gravitational wave observatory, so interferometry is right there in the name. Each LIGO instrument, so I should say I am part of LIGO Labs, so my exposition will be strongly focused on LIGO, but Virgo is very similar, although the inner workings are slightly different, but I'm not an expert in that. So, okay, so each LIGO instrument is based on a 4-kilometer Michelson dual recycle Michelson interferometer. I'll unpack some of this in a little bit. We can measure gravitational waves locally and transducing them into a digital signal, which is a difference from other observations or evidence from gravitational waves, for example, for binary pulsars that we had before. Okay, and what we measure and record is this local change in length over length, so the strain, and we call it sometimes differential arm mode, which is the difference between two arms over the original length of the arms as the gravitational wave goes through. Is the idea of this sort of measurement new to any of you? The million-dollar question. I have an answer. Okay, so there's two, like in many things in relativity, there's two equivalent descriptions of what's going on here, which correspond to different gauges or two different frames of what's happening. When we say that gravitational wave stretches and squeezes the space between the mirrors, but it's not actually moving the mirrors, and that would correspond to stretching and squeezing the ruler and so on, and the wavelength. We're using the TT gauge. It's called the transverse traceless gauge. So it's a particular set of coordinates and way of writing the equations that describe it in that way. Okay, and in that case, the coordinate distance between the objects is not changing, but the proper distance is. In that case, what's going on, let's see if I get it right. In the TT gauge, the light it effectively gets redshifted and blue shifted as the gravitational wave goes through. And it acquires a phase shift. And that's what you measure in the end. The mirrors do not move, but the light does get stretched and squeezed. It's blue, so in that picture it does. And because it's basically redshifted and blue shifted as the gravitation goes through, the phase it acquires around a round trip is no longer what it would be otherwise. So you think of it as the light actually getting stretched and squeezed in a sense. In the other description that we use, and I think the confusion comes because we switch back and forth between the two languages and never clarify this. You can describe the whole process locally in the local frame of the interferometer as the gravitational wave literally just moving the mirrors, not space stretching and squeezing between. Okay, you can switch your perspective, and you can write in some language. You have the masses at the end move with respect to the central beam splitter. In this case, the coordinate location of the masses is changing, and then you can describe that process as you would any other process that just changes the coordinates. And in that case, the light doesn't get blue shifted or red shifted, it's just a change in distance. And you get a phase shift that's exactly the same that you would have computed in the other picture in the TT gauge. This is a sort of subtle point that I think many of us within the community also don't appreciate. The observable is the same. We use the local frame of the detector because all the other physics is not gravity, all the electromagnetic equations, the description of the laser, everything happens just like in regular classical physics, Newtonian, or the Maxwell equations you apply in the same way that you use in flat space, with the only difference that you consider the mirrors are moving. And so that's what the instrumentalists like to use. So they actually just think of the masses moving. But the fuller picture is richer than that. And so that's what the other transverse traceless description is, in which the space-time does get shifted. So there's a dual description of this process. They both give you the same phenomenology. Does that answer your question or confuse you more? It should confuse you a little bit, so you go look it up. Okay. All right, so before I go into some of the details of actual instrument like this is designed, let's try to think about what the interaction between the interferometer and the gravitational wave is. So this is one of our LIGO detectors. We have two, one in Hanford, Washington, in the western side of the United States, one in Livingston, Louisiana, in the east. So this one's Hanford in the east, in the desert. There you see this 4 kilometers that way, and it goes the same here. You have one of the end masses here. This is the center where the laser and the beam splitter are. And so if you just superpose the video I showed you earlier, here basically that's what's happening. So a gravitational wave comes, let's say, from right on top of the interferometer. It's aligned, so it's stretching and squeezing this space in directions parallel to the arms. Okay, so imagine the gravitational wave is just coming from the zenith, coming down, and it's stretching and squeezing along the arms. Then the response of this instrument will be maximal, because what the LIGO measures is the difference in length between the two. So this sort of, if you're stretching one of them right along that direction and squeezing the other one exactly aligned, that's a maximal effect that you can have, okay, a given gravitational wave. However, if the orientation is different, for the same gravitational wave, the detector will not be as sensitive. For example, if it came from the line bisecting the angle, so if it came along this direction in the plane of the interferometer, and it was, let's say, stretching and squeezing vertically and doing it so horizontally, so it has the same effect on both arms. Do you see? So if you project these red lines onto the arms, it's at one moment doing the same to both of them. So there's no relative change in length. And so this gravitational wave is not seen by this instrument. So there's an angular dependence of the sensitivity of each instrument to a gravitational wave, depending on where it comes from. And it comes directly from the geometry of the measurement that we're doing and the geometry of the gravitational wave, how it's changing length. So we can represent this by a plot like this, in which you imagine that your detector, your interferometer, is located in the center as shown here by these two red lines that represent the arms of the instrument. So we're measuring the difference in the arm lengths. And then you can use a radial coordinate to represent how sensitive your instrument is to a gravitational wave coming from a given point in the sky with respect to the interferometer. Okay, so a signal coming from here, it affects the, so a cross-polarized signal coming from this direction, it affects these two, it changes the length in the arms maximally, and so you have a large response, whereas if it was coming from within the plane, it would actually affect both arms the same, and you don't measure it at all, so there's no sensitivity there. Okay, this is what we call the angular sensitivity or antenna pattern, and it relates the geometry of the instrument to the geometry of the gravitational wave. Okay. Mathematically, what's going on is that if the detectors are small with respect to the wavelength, we can think of it as just a linear, as the measurement process as a linear filter or that's applied to the gravitational wave, and we can forget about frequency dependence and so on, so we just look at the geometry of which directions get stretched and squeezed at any given time. And so what happens is that the output of the detector H, so indices here are tensors, I hope you're all familiar with Einstein notation. You can write as the projection of the gravitational wave H, and remember this tensor HAB, it encodes the directions in which the gravitational wave is stretching and squeezing space, and you want to project that onto your detector. So the detector tensor, such that the readout from the interferometer is really just the inner product between the gravitational wave tensor and this detector tensor. Okay, and then this gravitational wave tensor, again, you can decompose into a plus and a cross part, just the two polarizations. Okay, and so in the end, you have that the output that the detector reads, you can write as the plus part of the gravitational waveform times some factor f plus that encodes the geometry of the detector and the gravitational wave, and the same for cross. So there's two terms. So the gravitational wave intrinsically has two polarizations. Each of them interacts with the geometry of the detector in some particular way. The measurement that we get out is just the double contraction of the two things. These factors f are precisely the antenna patterns. They're precisely this angular structure that I showed you before. And you can go and write it down, and if you set some coordinates, for example, in the detector frame, and you say my arms are along the x-axis or the y-axis, well, you have to first pick a specific form of what the detector tensor is. And for LIGO and Virgo that are differential arm detectors, so they measure the difference in arms, you can show that you can write this detector tensor as really, it's just the difference in the magnitude of the x arm and the difference in the magnitude of the y arm, where xa and x and ya, they are vectors lying along the lines, along the direction of the two arms. So this is just encoding the fact that the instruments are measuring the difference in the two arm lengths, if that makes sense. And if you pick the right coordinates in the frame of the interferometer, then that detector will just look like this. It's just you're taking the difference between the two. Again, so you can pick a frame and you can write down what those f factors would look like coming from this tensor, and you would have some function of the location in the sky, the angles around the detector, and that's what gives you these sensitivity antenna patterns, encoding they encode the angular sensitivity of the detector to rotation waves from different directions. Is this sort of clear? Okay. All right, so just to summarize, the output of an ideal detector to a gravitational wave is a contraction. So detector I gives me an output h of t. Okay, that's a function of time. It's just the contraction of the gravitational wave, which is this amplitude function waveform ha of t times this tensor encoding the effect of the gravitational wave, which is what I showed you at the very beginning. And here a can be plus or cross, and we're summing over them. And then you contract that with the detector tensor, and that gives you something that looks like f plus, h plus, plus f cross, h cross. And this H is H of t, plus and cross. The polarizations are determined by the source. It's what we call the waveform. Okay, so it has no information about the detectors. It's just what intrinsically the gravitational wave is. And then these F terms encode all the information about the geometry of the measurement process and relative to the gravitational wave. So this will depend on where the gravitational wave is coming from and so on. Well, I mean, you have to pick a particular orientation. I think it's hard to say in general. I guess by eye it could look like it's more sensitive to plus or something. But this is defined in some specific frame, right? So what we mean by plus and cross here, for those to have a meaning, you first have to define the axes, right? So here we have pick some axes that are aligned with the detector. And then if the gravitational wave is stretching and squeezing along those axes, yeah, the sensitivity will be in general greater. But at a given source, you know, it doesn't have any, it's not like it's more sensitive to some sources or others, right? Because any arbitrary source will be oriented in some arbitrary way and will decompose it into these two ways. I think they're roughly equally sensitive. I don't know. The thing to bear in mind is that the two LIGO detectors are actually effectively co-aligned or anti-aligned. So if you grab one Hanford's here, Livingston's here, if you were able to like transpose them or put them together, they will be essentially along the same axis. So they actually only measure some linear combination of the polarizations effectively between the two, if that makes sense. You can think about it a bit more. So it depends on what frame it is. The LIGO instruments only measure one polarization, which is some linear combination of plus and cross in an arbitrary frame. Is that confusing? Remember, the polarizations are, so how much plus or cross you have, you can't really say until you orient your frame, right? The same way that if I have an electromagnetic wave and it's oscillating the field in some direction, right? I don't know if it has how much vertical or horizontal component it has until I fix some frame in which I define that. So these plots are deceiving because it's just in the frame of each of the interferometers. But if I want to know how sensitive I am to an arbitrary gravitational wave, I have to take into account that I have interferometers on the surface of the Earth, and each of them has a response like this relative to itself. So I need to grab the gravitational wave and decompose it into the polarizations for each interferometer, if you wish, and then see how much it responds to it. So because the two LIGO interferometers are aligned, you'll find that that decomposition tells you that they are sensitive to the same part of the gravitational wave from the source, so a single polarization that they define by that frame in which they're aligned. Anyways, I think I took your question to a more complicated way. Yeah. Yeah, so these are omnidirectional instruments largely, right? They have some blind spot, but it's not like a telescope that has some field of view, right? I mean, some narrow field of view. It's largely they're sensitive. An arbitrary gravitational wave will have, let's say, equal amounts of these, and so you take each of these, square them, and take the square root, and you get something that looks like a peanut, and we basically have sensitivity from everywhere in the sky, right? If it has both polarizations, yeah. So unless it's exactly aligned so that you are in this situation, then yeah. And if you have a network, the several interferometers are, but yeah. So this is both a blessing and a curse in a sense, because just like microphones, you know, it can record signals from everywhere. Each instrument can, largely speaking, modulo this, which means that when you get the data, you don't know where it came from. right? So if you want to reconstruct the sky location of a source, you're going to need to either tease out this polarization content very well, or actually make use of the timing between the network of interferometers to triangulate where the signal came from, just like with microphones or your ears. Okay. Any more questions about the ideal case? So in the ideal case, this is just very nice, because the detector just gives you the output of the contraction. It's a projection of the gravitational wave on each instrument. If you have several, as I just mentioned, you can reconstruct where it came from. You can reconstruct the orientation. You can measure the properties, the frequency and amplitude of the gravitational wave as a function of time, and that helps us identify what source it came from and so on. In reality, the measurement process and the data product are way more complicated than this. Okay, so we have 3 working large-scale real interferometers. As I mentioned, the 2 LIGO instruments in Hanford and Livingston. We have Virgo in Italy, which is 3 kilometers long instead of 4. Geo is 600 meters. We don't really use it for astrophysical observations. Kagra is under construction in Japan, and LIGO India is planned and moving ahead to join in like 10 years or so. Yeah, and it's very exciting. There are very interesting differences with, like, LIGO doesn't use, but Kagra Ford talks as well. Anyway, so the actual instruments, they're massive and complicated machines. I just want to give you an idea of what they look like in real life. This is, as I mentioned, the Hanford detector. You have here's where the laser gets created, stabilized, and so on. There's all the beam splitters that send down the inside this, that have 4 kilometers a long distance, and in the end there's an end station mirror that bounces the laser light back. So this is the site in Hanford that's in the desert. The other site is in, let's see, it should change soon to show you the swamps in Louisiana. So they're in very different environments, but they're designed to be clones of each other in almost every single way, besides the fact that different people work on them. And this is for both redundancy in the measurement and sky localization and so on. Okay. So LIGO has 4 kilometer long arms. At the peak, this meant that the gravitational wave signal from 15 to 14 that caused a strain of 10 to the negative 21 changed the distance, the length of the arms by 10 to the negative 18 meters. So this is like 1,000 times smaller than the nucleus of an atom, so we'd like to say. So it's extremely small and precise measurement. Was at the peak. So these 4 kilometer long arms are kept at a vacuum of a trillionth of an atmosphere to produce that. So what you see here is a concrete enclosing that protects these vacuum tubes that you saw in the video before. Those metal tubes that are run inside were baked for a month, so you run current in them for like 30 days to extract all the gases. So when LIGO was constructed, to extract all the leftover gas and particles that are left in the material, and then they were pumped for a very, very long time with different techniques to achieve this trillionth of an atmosphere, and then they were shot. So it has, I don't know, venting this is an extremely, I think it's the second or third largest vacuum at this level in the world. So it's very, there are valves that isolate the arms every time that some work has to be done on the optics or other part of the instrument. We can isolate the arms so we don't have to fill it with air and vent it back out. The main component is an extremely stable infrared laser of 1064 nanometers. It can operate at maximum at 100 watts, although we don't use it that high at this point because the instrument is not at that stage yet. The laser looks something like this. Well, it's located here. It looks something like this. Well, there's all this optical stuff to stabilize the power and the phase and make it one of the most stable in the world. And then, well, it bounces around here, and it goes into interferometer right here, actually. This is the input port. So it shines. It's fed into the system in there. Once it's inside, it's actually kept circulating so that there are 750 kilowatts of circulating power, even though we start with 200 watts. Well, at design operation parameters. We have mirrors in the center, at the end, and you'll see there's different components, but we have several mirrors, and these are polished to nanometer level to be some of the most perfect mirrors ever made. They have several coatings and other specific optical properties that make them really technological marvels. And then all of this is mounted on several layers of active and passive seismic isolation to separate the mirrors and the whole optical system from the motion of the ground and the environment. The simplest version of this is the fact that the mirrors are hanging from a quadruple pendulum, so that's a pendulum and a pendulum and a pendulum. So 4 stages. That means that when the ground is moving, the mirrors will actually not respond to that frequency. And this itself is in a large vacuum chamber that has active seismic isolation for some frequencies, so just like noise-canceling headphones can record the motion of the ground at the very bottom and actuate on it at the top to cancel it out. So this is, well, I find it very impressive because I'm not an instrumentalist, and to me it's like magic. Anyways, here's just to give you some idea of the complexity of the instrument. It's a steps up from the basic Michelson idea that I showed you before. Okay, the main concept is the same, but it's vastly more complicated. So the laser comes in this way, it bounces around this whole optical system, which, well, okay, let's look at the broad features first. So it comes in here. This is the beam splitter where the beam gets split into 2 and travels down one arm and the other. Each of these is 4 kilometers long. You have the end station mirrors, which bounce the light back. You also have intermediate mirrors here before the light reaches the beam splitter again. These form what are called Fabry-Perot cavities. So there's 4 kilometers in here. What it does is it essentially forms a bottle of light. So light keeps bouncing back and forth here around 280 times. If you, I guess, I don't know how they measure that, but it's a given photon, I guess, bounces around for a long time in here, building up the power in this optical cavity that's 4 kilometers long. And then it gets reconstructed here, and light gets sent down this way where it's read out here with this photodiode. There are also mirrors here. That means that some of the light that would otherwise go back to the laser gets fed back into the system, which is part of the reason why in the end there's much more power circulating than we actually put in. And then we also send back some of the light here with this signal recycling mirror. Anyways, I'm not an expert in the instrument, but I just want you to understand that these are very, very complicated machines. And it's really takes a lot of effort to run them, and you have to keep in mind the complexity of the system and everything that it entails when you're analyzing the data that comes out of it. To give you some more real-life input here, this is what the main mirrors look like. They don't look like mirrors to us because they're mirrors to infrared light, okay? These are some of the vacuum chambers and this seismic isolation systems. Let's see. My main goal with this, I want to give you an idea of scale. So you'll see a person in a little bit, I think. I don't remember my own videos. So let's see. Maybe not. Oh, there we go. Yeah. So this is where the beam splitter is, where the light gets split into 2, and then it goes down 4 kilometers that way and 4 kilometers the other way. Why all this stuff? Because when you build a very sensitive machine to detect these very small displacements, 10 to the negative 18 meters or so. You also make a very sensitive machine that's very sensitive to everything else that wants to move those mirrors around. So noise is our bane, is our enemy, okay, and it's what dominates the output of these instruments. There are several fundamental sources of noise. So there's a physical processes that will make your measurement noisy, even if you're the best at building these machines that you could be. Okay, so of course, there are seismic vibrations, just because the ground is moving at low frequencies, is shaking all the time. Okay, there are also what we call Newtonian gravitational noises. So it's just changes of density in the environment of the interferometer cause a Newtonian attraction between mass and the mirrors. Okay, so one thing is the ground shaking, and it's shaking the whole instrument in different ways, and this makes the mirrors shake. Another thing is if you have an object that's close to the mirror, it will Newtonianly attract it, okay? G equals m1 times m2 over r, or whatever. And that will create a Newtonian noise, a gravitation, just because these instruments are so sensitive that they're sensitive to that kind of stuff, which is mind-blowing when you think about it. Those two are mostly at low frequencies, okay? Then you have, obviously, even though we have perfect vacuum, it's not perfect, so there's some residual gas in the arms that may cause scattering or jitter the mirrors. You have thermodynamic fluctuations on the surface of the mirrors, just the fact that the mirrors are operating at room temperature, not at 0 Kelvin, means that there's Brownian motion on the coatings of the mirrors, and this gets imprinted on the face of the laser and can confuse the measurement. Okay, so we're sensitive to the atomic motion on the surface of the mirrors. And then you have quantum sources of noise that come from the fact that light is not really a coherent wave made out of photons. So you have radiation pressure that comes from the fact that, radiation pressure and photo fluctuations and shot noise, sorry, that both come from the fact that light is a quantum phenomenon, and it has to do with the fact that photons arrive at the photo detector and and hit the mirror in a stochastic way. So it's a Poissonian process. So it's like a pitter-patter of photons arriving, which make the mirror and the output jitter in some way that it would not happen if it was a coherent classical process. So there are very advanced optical techniques to try to mitigate all of these, especially these quantum effects that I'm not an expert, but it is fascinating if you want to look into it. Anyways, these are just some of the fundamental sources of noise. Of course, all sorts of other things. In the end, what we do to represent this is to say for a given frequency of measurement, so we have a measurement that should only ideally be sensitive to a gravitational wave